Okay guys, let's continue. This time I asked you to watch a video which I prepared and uploaded to YouTube. The video is about the traveling wave equation, right? In that video I didn't derive the equation. I introduce it slowly, right, so that everything would be clear. And so now we just need to review major points of that video, and then we just need to start applying it for different traveling waves, right? Okay, so let's start. Okay, I prepared a few things, right? So let's assume that this is this is the traveling wave equation, right? Which we discussed in the video, right? So what do we have here? A, right? So y, it's a function of two variables, right? X and t, and we have a sine kx plus minus omega t plus phi naught. And now let's just discuss it term by term. A, it's the amplitude of the wave. Basically, it tells us the maximum displacement of a particle of a media, right? When a wave propagates, right? Maximum displacement, amplitude. Then periodic function, sine, right? Then kx. So what is k? Well, let me use this problem. What is k? I will put an arrow like this. K, it's a wave number. For many of you, this is a new quantity, and you probably have never heard about this quantity, right? Wave number. Physical meaning of this. Okay, maybe let me first write it. So it's a wave number, right? Physical meaning of that. It's basically spatial frequency. Right, it's a spatial parameter, spatial quantity. Spatial frequency, what is that? It's just basically number of wavelengths that you can fit in 1 meter. Spatial frequency. But strictly speaking, it is introduced as a number of wavelengths in 2 pi radians. But still, the meaning is the same. It's basically spatial frequency. Right. Okay, and underneath I will write meaning spatial frequency, right? Okay, then x. You know what? Let me use maybe still blue. X is temporal, spatial variable. Spatial variable, of course, position x, right? Spatial variable. X is the spatial variable. Right. Okay, so basically it means that all spatial information about the wave is in this term in kx, right? So if you want to find any spatial parameter or spatial quantity which describes this wave, you must find it from this term, All the spatial information is hidden over here. Then, all right, and you know what? Let me start filling out this table, right, which I prepared. So first, variable, spatial variable x. I can add here, so x, it's a spatial variable. Spatial variable, right. Then, okay, let me close this, right? And then I just now introduce wave number k, which is spatial frequency, right? So we introduce also k as 2 pi over lambda. That's the definition of a wave number, 2 pi over lambda. The meaning is spatial frequency, right? Wave slash number. The meaning, spatial frequency. Oi, the wrong symbol. All right, so it's a spatial frequency, right? Okay, and then I will introduce temporal things, and here some additional. Okay, so then omega t. All temporal information of the wave is in this term omega t. So what's the meaning of omega? Omega, okay, maybe I will use different color, right? Omega. What is omega? The name of the omega is angular frequency, but the physical meaning is just a temporal frequency. So omega, angular frequency, right? And the definition of angular frequency, omega, right, over here I will write, because this column is about frequency, spatial frequency k, and now I will add angular frequency, right? So I will write here omega, and by definition is very similar to the spatial frequency. 2 pi over lambda. What is lambda? Lambda, it's a spatial periodicity. Basically, it's a distance over which wave reproduces itself. Now, in exactly the same way, okay, in a similar way, angular frequency is introduced. 2 pi divided by, but now divided by temporal periodicity. What is temporal periodicity? It's a period. Temporal periodicity, it's a period of time over which the wave reproduces itself. Right, so angular frequency is introduced as 2 pi divided by time. So it's a angular frequency, right? And of course, the meaning, it's a temporal frequency, right? So you see, here I want to keep all my temporal parameters. Here I want to keep all my spatial parameters or quantities describing the wave, right? Okay, so angular frequency, again, I'll write the meaning underneath. Okay, it's the meaning, this temporal frequency. Right. Okay, of course, we discussed all that diligently in the video, which I asked you to watch. Right, then what is t? T, of course, time, right? But in these fancy terms of spatial and temporal, it's just temporal variable. X was spatial variable, right? Describe the wave in space. Okay, in space. And temporal frequency, it's a, temporal variable. It's a variable which describes the wave in time. All right, so temporal variable, right? Okay, so now I can add this temporal variable over here. So t, temporal variable, right? Okay, as I promised, here only temporal variables, temporal quantities, and here only spatial quantities. Okay, then this plus minus. So minus means that this wave propagates in a positive x direction. This variable, this x, this spatial variable, tells us along which axis this wave propagates. If we had, for example, here y, it would mean that this wave propagates in the y direction, right? Then if we had here z, for example, right, z, kz minus omega t, it would mean that that wave would propagate in the positive z direction. So whatever variable you have here, it just tells us that along that axis, our wave propagates. So be careful, because sometimes on the exam, if I give the problem like this, instead of x, I can use y or z, right? But of course, the rest of the analysis will be exactly the same. Right? So propagates, which way I wrote just a second, travels in plus x direction. And plus means that if you have a plus kx plus omega t, it would mean that that wave travels in minus x direction. Travels in minus x direction, right? Okay, phi naught, it's the initial phase of the wave. This whole bracket, kx plus minus omega t plus phi naught, this whole thing is called the phase of the wave. right? Phase of the wave. And this is just initial phase, right? Okay, again, amplitude, all the spatial information of the wave is in kx, right? And again, if you know k, you should be able to find lambda immediately without any significant troubles, right? 2 pi divided by k, that will be lambda, right? Then all the temporal information is here. And if you know omega, you can find period of the wave immediately without any troubles, right? Period will be equal to pi divided by omega, right? And this, I forgot to add, let me add this, lambda. Periodicity. Lambda is of course it's a wavelength, but the meaning of the wavelength, it's a spatial periodicity. It's a distance over which wave reproduces itself. Of course, wave length, and the meaning, it's a spatial periodicity. Right, and over here I can add a similar quantity, but for a similar temporal quantity. What is temporal periodicity? Basically, it's a period of time over which wave reproduces itself in time. It's a period, right? So, all right, t equals, of course, the meaning, it's a period, right? And the name is a period, but physical meaning, it's a temporal periodicity. Temporal periodicity, right? And again, you see the way we introduce this frequency, spatial and temporal frequency, 2 pi divided by spatial periodicity, and omega equals 2 pi divided by temporal periodicity. Okay, then the last piece before we start solving problems. Look. Okay, we divided all this set of parameters, quantities into spatial and temporal, blah, blah, right? But what about the speed? Speed of the wave. Speed, just in general, what is speed, right? It's you need to take the distance divided by the travel time. L divided by t, you will get the speed, right? The same here, right? So you see, the speed, in order to find speed, you need to mix spatial parameters, spatial quantities, distance, with temporal quantities, right? Quantity, time. So here the same, right? So in order to find the speed of the wave, right? So you need to mix quantities from here and there. So you need to mix quantities, spatial quantities with temporal quantities, right? So as a result, speed works as the bridge between the spatial parameters and temporal parameters. We're going to practice in our problems, right? So, but you remember, speed works as the bridge between the spatial parameters and temporal parameters, right? And there are two ways of, we can say there are two formulas which can be used to find the speed of the wave, right? So let me write here underneath, speed of a wave, right? So there are two ways of finding speed. V equals, as I said, you need to mix spatial parameters, okay, spatial and temporal parameters. So one way, you need to take omega, which represents the temporal world, and divide it by k, which represents the spatial world. You see, it works as the bridge, right? So you need to mix these parameters. So it's a first way of finding V. The second way of finding, if you found from k lambda, and if you found from omega t, you can find a wavelength like this. So you need to take lambda and divide it by t. Or since t is a reciprocal of frequency f, you can also find it as lambda times f. Again, you see, lambda, it's a spatial periodicity from the spatial world. T, it's a temporal periodicity from the temporal world, right? So let me frame them, these, like this, and like that, right? And after this, we can say, yeah, we reviewed everything, and now let's start looking at the problems. So the first problem which I want to discuss is problem 14 from chapter 16, right? 16, 14. And what is given? This plot is given, right? And what do we have in the plot? D, right? Displacement of the particles, for example, on, I don't know, on the cord, or all right. So D instead of Y, right? In centimeters versus time, right? And first of all, I want to ask, which type of curve do we have here? You remember in that video, which I asked you to watch, at the end we discussed, because this is the function of two variables, x and t, right? And analyzing that is not trivial. So as a result, researchers usually divide analysis into two steps, right? So you can first, for example, freeze x and observe what happens with the wave in time, right? Or you can freeze time and observe what happens with the wave in space. In this case, what? We have time information, right? So it means that x is frozen, and what we observe is a history graph. Example, again, as I told you in the video, example, it's like a boat on the surface of the lake, right? So wave propagates, right? But the boat doesn't move. It doesn't travel. Boat doesn't travel, right? It just moves up and down, oscillates, right? So if you, so basically x is fixed, and if you watch on your watch, if you watch and if you keep track of time using your watch, you can plot graph like that, right? So the boat goes down and then up, but x is fixed. So basically, this is the history graph, right? History graph. When x is fixed, and you observe what happens with the wave, that type of graph is called the history graph. So let me write this down. So this is effectively the history graph. History graph, right? So x is fixed. Let me write x equals 0, and I will emphasize it's fixed, right? Right. And we also know that this wave travels with speed of 2 meters per second to the problem says traveling left, right? Basically, it means it travels in the negative x direction, right? So which way I wrote? Okay, wave traveling left at 2 meters per second, right? So v equals 2 meters per second, right? Okay, right. I think we have everything. Yeah, right. Time is in seconds, and displacement d is in centimeters. So, and we need to find a bunch of parameters. So let's start with the first one. A. We need to find amplitude. Amplitude is trivial. So here's the amplitude. So this is A, this is minus A. So the amplitude is 6 centimeters. Usually amplitude you can get from the graph immediately, right? So no troubles, right? So A equals to 6 centimeters. Then B. What else do we need to find? Frequency, F, right? So we need to find this frequency, right? Okay. Frequency, it's a temporal quantity, right? So we should be able to find any temporal quantities easily from this graph, right? We might have troubles with finding spatial quantities, but we will talk about in a few minutes. So F, in order to find F equals, it's a reciprocal of the period, right? So if we can find the period, we can find frequency easily. How can we find period from a history graph? It's trivial, because the time interval between crests, right, on the history graph is the period. Because again, what is period? Period is temporal periodicity, periodicity of the wave in time. Periodicity of the wave in time, because we have a history graph, right? So this period of time is the period. So let me show that this is t. So from the history graph, you should be able to get period immediately without any troubles by just looking at the graph, right? Okay, so I can write, right? So t equals what? 0.8 seconds minus 0.2 seconds. 0.8 seconds minus 0.2 seconds, you will get 0.6 seconds. And I will write from the graph. You can see immediately from the graph. And as a result, what is frequency? Frequency equals 1 over t. So it's 1 over 0.6 seconds, right? 0.6 seconds, it's a 10 over 6. 10 over 6 hertz, right? Hertz, it's 1 over seconds. Right? Of course, you can calculate approximately, it will be 1.67 hertz, right? Okay, so as I said, since f, it's a temporal quantity, finding it very simple. What next? What is next? We need to find wavelength. So part C, we need to find lambda wavelength. The name is wavelength. What's the meaning? Spatial periodicity. Okay, so now the question is about spatial parameter, but we don't have we don't have any information except for this graph was made when x equals 0. So x is fixed. As a result, spatial or pretty much all the spatial information is missing. So what we have here, only temporal information. Spatial information is frozen, right? So what can be done? Because now the question is about spatial periodicity. And you remember at the end of this review, I told you, guys, the speed works as the bridge between the world of spatial parameters and the world of temporal parameters, because in order to find speed you need to mix both of them, right? Omega from the temporal world, k from the spatial world, right? Spatial world, temporal world. So, and we know information about the speed. So information about the speed allows us to move and find parameters from the spatial world, right? So now, since we need to find spatial periodicity, we have to use V, right? Okay, so, and we have this way of finding V, or that way of finding V, right? So let's use, since we found frequency, right, we need to find lambda, and V is given, so let's use this formula, right? So I think this will be the easiest. So V equals lambda F, right? And, okay, let me write, so V works as a bridge, right, between the world, which way I wrote, just a second. Just as a bridge, right. And so what we need to find? We need to find lambda. So let's write lambda equals V over F. So V equals 2 meters per second and divided by F. F is, okay, I don't want to use this. I want to use 10 over 6. Right, 10 over 6. 1 over second. Hertz is 1 over second. 6 goes upstairs, right? 10 stays in the denominator. As a result, we'll have what? 6 over 5. 6 over 5. Right. 6 over 5 meters, or approximately 1.2 meters. So that's the wavelength. So spatial periodicity. So over that distance, 1.2 meters, wave reproduces itself, right, in space. And we also found period over 0.6 seconds. 0.6 seconds, wave reproduces itself, right? Temporal periodicity, spatial periodicity. So what's next? Yeah, at this point, actually, part C, the problem is over. That's problem 14. But I feel like not completely satisfied. We still can find tons of other parameters, right? So so now I'm adding additional parts, additional questions, right? So let's find, for example, omega, k, and then eventually find naught, and then eventually we can write the whole traveling wave equation. Let's do it. Again, as I said, at this point the problem is over, but I feel like let's continue. So now, right, I will put some sort of like a line end. So officially problem is over, but I want to add more questions. A, B, C. Now D. What I want to find in D? Let's find K, wave number. K. Let's find wave number, spatial frequency. K. Let's find K. And of course, by definition, that's how we introduce K, 2 pi divided by lambda, spatial frequency, right? So lambda we already found, so now finding the rest of the spatial parameters can be very easy, right? Okay, 2 pi over lambda, so 2 pi over 1.2, right, 1.2 meters, and you will get okay, I just it will be pi divided by 0.6 inverse meters, right? Okay, so I will keep it in terms of pi's. It's not a big deal. So now we know K. Again, why I'm trying to find this? So I want to find K, I want to find omega, so I can write the equation. So we found K. Now what's next? Most likely omega. Let me check. Yeah, let's find omega E. Now let's find angular frequency. The name is angular frequency. The meaning is it's just basically temporal frequency, right? Spatial frequency, temporal frequency. Again, by definition, omega is 2 pi divided by temporal periodicity. Temporal periodicity is a period. And we found period in part B. Period is 0.6 seconds. So 2 pi divided by 0.6 seconds. 0.6 seconds. All right. So pi divided by 0.3. Pi divided by 0.3. Units 1 over seconds. Okay, actually it's a radians over seconds, right? Radians over seconds. So omega, and so basically we're almost ready to start writing down the equation. And actually let me write it down, and then what else we need to find. So now I can write that d, because that's what we have, displacement d. Here we had y, right? But here in the problem d, as a function of x, and t equals, okay, amplitude, let me just write everything in terms of still parameters. Sine kx, our wave still propagates in the x direction, so that's why I use x equals 0, right? So if wave propagated in the y direction along the y-axis, we would have y. If wave propagated along z direction, we would have z. Then now plus or minus, the problem says that wave traveling, okay, let me underline it, left. To the left, it means negative x direction. Negative x direction, we have to use plus, right? So we have to use plus. I made a big plus. Then omega t, so k we found, omega is found, and plus initial phase. And initial phase now shouldn't be 0, because initial phase 0 is only for the case when we have a pure sine function and at x equals 0 and t equals 0, wave crosses the origin like this and then behaves like a sine function. In our case, definitely it doesn't behave like this, so our initial phase is not 0. So let's find initial phase now. Right? So now it's A, B, C, D, E, F. Now part F. So let's find initial phase. Phi naught initial phase of the wave. Right? So in your homework there will be one problem where you will have to find initial phase. And here is the procedure. So what do we know? In order to find initial phase, you need to take any of the points which we have. So what we have? We have information about the wave at x equals 0. So we can take, for example, x equals 0, and we can take any point on this graph. Any. You can take this point, this moment of time, or this moment of time, but I don't want to deal with any other. Okay, the easiest point when t equals 0, right? But of course you can take t equals 0.2 and solve this equation, because at 0.2 you know the displacement is -6. So if you take this point x equals 0.2, d will be -6 and x equals 0, and then you can find for phi naught, but the equation will be more complicated. So the easiest point which you can use to find the initial phase is t equals 0, initial moment of time. And we know the displacement is 3 centimeters. So x equals 0, t equals 0, displacement is 3 centimeters. So let's use that point. All right, so let me write, let's use x equals 0, t equals 0, right? And at these x's and t's, d is 3 centimeters. d equals to 3 centimeters. So now we just need to plug into our equation and find phi naught, because x0, t0, amplitude we know, d is also known at this particular moment of time. So now let's write, so 3 centimeters equals, I'm just rewriting this, right? Equals amplitude 6 centimeters times sine k times 0, because x equals 0, then plus omega times 0, plus omega times 0, and plus our initial phase, which needs to be found, right? So basically we have 3 equals 6 times sine of phi naught. Okay, I will write it here. So 3 equals 6 times sine of phi naught. Phi naught equals arc sine of 1/2, which is pi/6. Okay, let me write this down. So as a result, phi naught equals inverse sine of 3/6. Okay, in radians, pi/6 radians. Okay, so at this point we can write down the equation, right? Maybe I can squeeze it underneath, although I don't like that. Right. Okay, let me fit it. Right, so dx t equals, okay, amplitude 6. Times sine k, where is my k? pi/0.6 times x, right? Then, okay, plus omega, where is my omega? Here, pi/0.3 times t, right? And plus our phi naught, which we just found, plus pi/6, right? So that's our traveling wave equation, which describes this particular wave, right? Okay, this is the history graph, right? History graph. Of course, if you fix time and plot x, plot wave when time is fixed, it's called a snapshot graph, right? But here we had a history graph, right? Okay, so you see, it's not that complicated, right? But of course, you need to be familiar with these formulas, and usually, of course, these formulas are given in the formula sheet on the exam. And as I noticed, usually students don't have significant problems if I give a problem like this on the exam. Right. So, next problem. It's not from the book, right? I just created it to discuss slightly different situation relative to what we discussed just now. So now let's assume that we have a traveling wave. And what do we know about this traveling wave? We have this plot. So what do we have? We have y, displacement of the medium, particles of the medium, right, in centimeters, right? And we have this sine function. And it's a y versus x, right, versus x. We have points 10, 20, 30. We have 5 here, minus 5 there, right? And we also know that this wave travels in the negative x direction to the left with the speed of 10 meters per second. First of all, we need to understand which graph do we have now. Over here, we had the history graph. Position was fixed. X equals to 0. As a result, we observed we had information about what happens with this point x equals to 0 in time. Now, what do we have? We have time is fixed, and we see the distribution of wave in space. What is that? How can we get a picture like this? It's basically you take a camera and take a snapshot. So how can we get a picture like this, right? You just take a camera and take a snapshot. That's why this graph is called a snapshot graph, right? So t is 0 fixed, and that is the snapshot graph. Snapshot graph. All right. Okay, here we had a history graph, and now we have a snapshot graph. So now we have plenty of information, spatial information, but temporal information is lost. We only know that this was recorded at t equals 0. So pretty much we don't have any temporal information. Right. Okay, so now we need to answer a few questions. So we need to find a few quantities. First of all, at part A, we need to find the wavelength, lambda wavelength, which is spatial periodicity. Where is my wavelength? Here, spatial periodicity, right? Again, what is spatial periodicity? It's a distance, of course, in space, over which wave reproduces itself. Okay, spatial information, it must be here. If you plot a snapshot graph, periodicity on the snapshot graph is the wavelength, right? Because again, wavelength is the spatial periodicity, and you see the distribution of wave, and you see the wave in space, right? Okay, so what? Where is wavelength? It's of course between these crests, for example, right? But I don't have space over there, so let me show it over here. So distance between this and this point, right? So this will be my lambda, right? That's lambda. Here, the distance between, for example, these two troughs, period, right? Because period is the temporal periodicity, and we have distribution of the wave in time. And here we have distribution of the wave in space, and the distance between, okay, for example, these two crests, wavelengths, or between these 2 points, of course, wavelength. Right? Okay, so wavelengths can be found just from the graph. 0, 20, so the wavelength is 20 centimeters. So lambda equals 20 centimeters, and I can write from the graph. We can get it directly from the graph. So then next, let's find the wave number. Again, I want to find all the parameters that we need in order to write down the traveling wave equation. Right, similar to this problem, but here again we had only history graph. Now we have a snapshot graph. So B, we need to find wave number. Okay, wave number, it's a spatial frequency, again spatial information, right? So we should be able to find any spatial information from what we have over here. And here, what's by definition? Okay, 2 pi over lambda. Lambda we just found. 2 pi over this gives us a spatial wave number. 2 pi over lambda, right? So it will be 2 pi divided by 20 centimeters. I think I will keep in centimeters. Yeah, 20 centimeters. So it will be pi over 10 and units centimeters to the power of -1. Actually, quite often wave number, these units are used to define a wave number, right? At least very often in spectrometers, these units are used. Then, okay, so now we have K, right? Kx, amplitude. Yeah, amplitude we will find. Actually, amplitude again, it's immediately you can see from the graph. So this is the amplitude, right? 5 centimeters. But anyway, so what's next? Let's find the period of the wave. Right, C, period, temporal periodicity, period. Again, the stretch of time over which wave reproduces itself. And again, the trouble is now with this quantity. What we have spatial information about the wave, only snapshot, only spatial information. T is 0, fixed, so we lost all the temporal information. So right now it looks like we don't have any temporal information, but we need to remember that speed works as the bridge between the world of temporal quantities and the world of spatial quantities, right? So and since we have we know the speed 10 centimeters per second, so this will allow us to move to the world of temporal quantities. So it means that we should be able to find period, right? Okay, so what can be used? We have speed, we have wavelength, so we can find period from here, right? V equals lambda over T, right? Okay, so let's use it. Right, so V equals lambda over T, or from here T equals lambda over V. Lambda, where is my lambda? 20 centimeters divided by V, 10 centimeters per second. 10 centimeters per second. Second goes upstairs in the numerator, and we will have just 2 seconds, period of 2 seconds. So we have 2 seconds. Right, so period is found, and now logically it looks like we need to find omega, the last missing parameter, right? Right, yeah. So the next one, A, B, C, now D, omega. Omega equals, okay, now let me write first that we need to find omega. And then I will find that omega, by definition, once you know the period, and we just found period, you can find omega like that, right? So by definition, it's a 2 pi divided by temporal periodicity, which is the period, right? So 2 pi divided by 2 seconds. So it will be pi seconds to the power of -1. Okay, of course, radians per second, but radians means nothing, right? What about the initial phase? Initial phase, we have sine function over here, right? And you see, since our wave at t equals 0 and x equals 0, displacement is 0, initial phase is 0. If you don't believe me, you can do exactly the same thing, right? So we have here 0, this is 0, this is 0, right? And in order to make this 0, phi naught must be equal to 0, right? So phi naught is 0, we can see from the graph, right? And, right, so let me write also. Phi naught equals 0, right? And again, I can say from the graph. From the graph, you can see, or you can calculate it, right? So now we can write the function, right? And again, I don't want to, where can I squeeze it? Right. Okay. So as a result, let me write first in general y as a function of x and t, a sine kx. Okay, our wave propagates to the, you see, speed to the left. So it means that to the left, minus x, we should have plus omega t plus phi naught, but of course phi naught is 0, right? Okay, so now y xt equals amplitude is 5 centimeters times sine k. Where is my k? Pi over 10 times x, right? Then plus omega. Where is omega? Omega pi times t, and that's it. So that's the equation which describes this wave, right? So time dependence, x dependence, time dependence, right? And that is just a snapshot graph describing this wave at t equals 0. Of course, you can draw a snapshot graph at t equals 1, 2, and so on, right? Or you can plot a history graph if you fix x, right? And again, if for example, let's say speed, let's say a velocity pointed that way, right? If wave traveled in the positive x direction, right, we would have here minus, right? If these were z, for example, z-axis, we would have here pi over 10 z. If we had here y, right, so it means that wave propagates along the y direction, we would have here y. Again, every time this coordinate, this x, in this case x, tells us along which axis a wave propagates. Okay, enough of this problem. Now let's look at the last one. Okay, and the last problem, again from chapter 16, but problem number 12. Okay, let me erase this. The first, finally, I can erase the first problem, solution of the first problem. Right. So that is 1612. Right? Yeah. So we have a traveling wave. So we have a wave propagating in the negative y direction, right? Yeah. Wave traveling in minus y, okay, this is minus y direction. Then we know that wave number of that wave is, okay, let me grab this. So wave number is 5.5. Units of wave number is in the reciprocal of meters. Yeah. Right, so radians per meters, or just sometimes, very often, we write meters to the power of -1. But of course, since we introduces 2 pi over lambda, so strictly speaking, it's a radians over meters. But so let me write just meters to the power of -1, because that's how we usually write it, or centimeters to the power of -1. Then omega, angular frequency, right, which is temporal frequency, right, omega, and the value is 72. 72, again, it's radians per second, or you can write centimeters to the power of -1, right? But omega we usually write as radians per second, right? And that's it. And initial phase is 0. Initial phase is 0, right? So now, it's not a question, but I present the problem in this way. So now, after writing these parameters, I want to write the traveling wave equation, and only after that we will start solving problem, right? Traveling wave equation. So displacement d, of course, in general, you remember it's a function of something, right? In a second I will fill it. Amplitude. Amplitude is also given. Amplitude is, what is the amplitude? 5.2. Amplitude is 5.2 in centimeters. 5.2 centimeters. Right, so as a result, right, so what we have, amplitude is 5.2 centimeters, right? A, then sine. Then next, kx, what is k? 5.5. 5.5. Now I have to pause, because very often at this point students start making unnecessary mistakes. Force of habit of writing x, but now the wave propagates along y-axis. So here, instead of x, we have to write y. Y, right? Okay, then plus or minus. We have plus if wave propagates in the negative y direction, and minus if wave propagates in the plus y direction. In our case, wave propagates in the negative y direction, so we have to put plus here, right? And omega t. Where is omega? Omega is also given, so 72 times t. Initial phase is 0, so that's the traveling wave equation. And now I can write, so the function of t, of course, but now instead of x we have y, because this wave propagates along y direction, right? So that's the traveling wave equation. Let me frame it, and now we need to answer questions which problem asks. All right, so first, part A. We need to find what first? Frequency. Let's find frequency, f. Okay, frequency, it's a temporal parameter, right? It's a number of cycles per unit time, right? In second, number of cycles per second. So it means that we should be able to find it from this, because that's where temporal information is. So we should be able to find it from omega. So let's write down the definition of omega again. Omega equals to 2 pi divided by t. That's how we introduce omega, right? Angular frequency. But we know that t and frequency are connected like this. Frequency is a reciprocal of the period, so it means that omega equals to 2 pi f, right? Okay, so we need to find f. Omega is given, so we should be able to find f. So as a result, f equals what? Omega divided by 2 pi. Very often students use W, right? It's not W. Again, it's not wrong to use W, but omega, it's sort of like a universal unwritten convention that angular frequency omega, right? So omega is 72 divided by 2 pi. Okay, so if you plug numbers, calculate, you will get 11.5 hertz. 1 over seconds. Hertz, 1 over second. So that's the frequency. Right. Next, what next? Wavelength. B. Let's find wavelengths. Okay, wavelengths, it's a spatial parameter. It's a spatial periodicity. It's a length over which wave reproduces itself, right? So it's a spatial parameter. So it means that we should be able to find lambda from K, because that's where all spatial information, again, here we have temporal information about the wave. Here we have spatial information about the wave. So from K, definition of K. 2 pi over lambda. So once you know K, finding lambda, it's a piece of cake, right? So K equals 2 pi over lambda. So as a result, lambda equals 2 pi over K, right? 2 pi over K, K is 5.5. 2 pi divided by 5.5. So we're going to get it in meters, right? Because units of K, 1 over meters. So lambda will be in meters, right? So what's the number? If you calculate it, you will get 1.14 meters. So that's the wavelength. Over a distance of 1.14 meters, wave reproduces itself, right? And the last part, speed. Let's find the speed, right? Again, usually if you know this, if the equation, traveling wave equation is given, it means that you know everything about the wave, right? So that's what we're trying to get. Usually what we want to know, what is the frequency, what is the wavelength, and then common questions, and then what is the speed of the wave, right? So let's find the speed. Wrong color, A, B, C. So now let's find the speed of the wave, right? And again, it travels in the negative or y direction, so the speed along the y-axis. So we have two ways. And again, speed, in order to find speed, you need to mix quantities. You need to take something from this world of spatial quantities and something from the world of temporal quantities. You can either mix omega and K or lambda and F, right? It depends what you have. In our case, we have complete freedom. We have omega and K, divide it and you will get the speed. And we already found lambda and F. Multiply this and you will get a speed. So in this case, at this point, either of these formulas, these and that, they're equally easy, right? So we have two ways of finding. So we can get V equals omega versus K, which is omega 72, divided by 5.5. And if you calculate it, you will get 13 meters per second. Meters per second. Or V equals lambda F, right? So what lambda is 1.14 meters times F. Frequency is 11.5 hertz. 11.5 hertz, right? So again, you will get 13 meters per second. Right, so you see these problems are not that complicated, right? You just need to understand the basic ideas, right? If you practice this problem, if you solve a few problems, usually these formulas are very simple, right? And on the exam, I tend to give a problem of this type on the final exam. And so far I notice any student who practice at least a few problems, they don't have any troubles solving problems like this, right? Okay, so that's enough for today. Thank you, and I'll see you next time.